All right, so this is section 9.4, day 1, video 2. It's kind of a mouthful. Um, we're just going to finish off these last two examples, and then we'll come back with 9.4, day 2 videos. All right, so number 4, calculus fluoride, a rare substance, reacts in such a way that the rate of change in the amount of fluoride left unreacted is directly proportional to that amount. You may ask yourself, is calculus fluoride a real thing? Yes, it is a real made-up substance. So, yes, it is a real made-up substance. It is rare. So it should start off the same way that we've done everything else. Write a differential equation that expresses this relationship. Integrate to find an equation that expresses um, excuse me, integrate to find an equation that expresses amount in terms of time. I should say the amount in terms of time. Use the initial conditions that the amount is 50 milligrams when t equals 0 minutes and 30 milligrams when t equals 20 minutes. All right, so let's start off by writing the differential equation. The thing that is changing is the calculus fluoride, so I'm just going to use capital F, and that is changing over time. And again, it is the fluoride which is changing. It's directly proportional to the constant of proportionality. So we'll go through our typical process. We'll divide by F, multiply by dt. 1 over F dF equals K dt. We can now integrate. So we've got natural log absolute value of F equals KT plus C. Go ahead and solve that for F. We will exponentiate both sides. So we are going to get F equals C e to the KT. Eventually you'll be able to figure that out. That's what's going to happen every time if you haven't done so already. All right, let's find out the value of K and the value of C because we need both of those. We should have the value of C. That's given to us. The initial condition here is 50 milligrams. And the new amount is 30 milligrams at 20 minutes, so we can use that to find K. So the new amount is 30 milligrams. The initial is 50. E to the KT, we're going to need to find K, and our time is 20 minutes. We can do this in one of two ways. You can either keep everything in minutes, or you can put it into terms of hours. It's probably easier just to go ahead and keep it in minutes in this case, but if you choose to put it in terms of hours, that would have been a 1/3. Let's go ahead and solve this thing for K. Divide both sides by 50. You get 30 over 50, which is 3/5. E to the 20K. We can then take the natural log of both sides, and we'll get the natural log of 3/5 equals 20K. Solving for K, we'll divide by 20, which is the same thing as multiplying by 1/20. Natural log 3/5 equals K. So there's our K value. So our function for the amount of fluoride is 50 e to the 1 over 20 natural log 3/5 times t. So now we should be able to use that to figure out the last two parts of this. Part B says how much fluoride remains an hour after the reaction starts. So an hour is going to be 60 minutes. So we'll plug a 60 in for t. So we're trying to find F of 60. 50 e to the 1 over 20 natural log of 3/5. It's supposed to be a 60 times 60. And plugging that stuff into your calculator gives us exactly 10.8, and this is in, what was this in? Milligrams. So the amount of calculus fluoride after 1 hour is 10.8 milligrams. Considering we started with 50 milligrams, and 20 minutes later it went down to 30, and then an hour later it went down to 10.8. This is obviously a decay problem. When will the amount of fluoride reach 0.007 milligrams? So that's going to tell us the left side of the equation this time, 0.007, because we're solving for t since it says when in the question. So it's 50 e to the 1 over 20 natural log of 3/5 times t, dividing both sides by 50, 0.007 over 50 equals e to the 1 over 20 natural log of 3/5 times t. Take the natural log of both sides. Again, no need to simplify anything as we go because we're going to do it all in one step when we plug this in the calculator. So now we get the natural log of 0.007 over 50 equals 1 over 20 natural log of 3/5 times t, and then solving for t, we will simply divide by the entire thing on the right side there, so we get the natural log of 0.007 over 50, that's the numerator, all over 1/20th of the natural log of 3/5. Plug all that stuff into your calculator, and this works out to be the time is 347.432 minutes. So it looks like that's just a little bit less than 6 hours to get down to 0.007 milligrams. All right, so that was a decay problem, excuse me. And one of the ways you're going to be able to tell whether something is a growth or decay is based upon what the exponential has in it. So e to the 1 over 20th natural log of 3/5, the natural log of 3/5, the natural log of something which is less than 1, or in between 0 and 1, I should say, is a negative value. So we are raising the e part to a negative value, which is going to make it decay. One more example. Let's see, this one's a little bit interesting because of how you can do this problem. Major purchases like cars and houses depreciate in value. That is, as time goes on, their value goes down. A reasonable mathematical model for the value of an object that depreciates assumes that an instantaneous rate of the object's value is directly proportional to that value. Okay, a lot of words there, really just telling us the same type of thing. Write a differential equation that says that the rate of change of the car's trade-in value is directly proportional to that trade-in value, and then we'll integrate the equation, express the trade-in value as a function of time. Again, all the same stuff. So you can call the trade-in value whatever you want to. P, V for value. Probably don't want to use T for trade-in because you're going to use a T in the denominator, although this is going to actually come up in another problem that we do. I'm just going to go ahead and use, let's use V, I guess, for trade-in value, for the value. So that means that the value is changing over time, and it is directly proportional to that value. Now, I am going to go ahead and skip the entire process that we've done every single time. We know that this is going to come out to be that the value is C e to the kt after going through the entire process. Obviously, if you have to do this on a problem, you will need to show the entire process, but at this point, hopefully you know where we're going with it. So, part B, suppose that you own a car whose trade-in value is presently $4,200. 3 months ago, its trade-in value was $4,700. Find the particular equation that expresses the trade-in value as a function of time since the car was worth $4,200. So there's actually 2 different ways you could go about doing this, and either one of them is right as long as you stay consistent. You can either consider the $4,200 as time 0. And if that's the case, because it does say presently, so you could consider that as your time 0. 3 months ago means that your time when you plug in for t is actually going to be -3 since it's time in the past. You could also consider that 3 months ago was time 0, 4,700, and then your time for t would be 3 if you used 4,700 as your c value. I am personally, because it says it, I'm going to use the 4200 as the current or C value, time 0. So we're going to talk about time in the past when we talk about 4700. So P equals 4200 e to the kt. And then it says 3 months ago it was 4700. So that would be the P value. So 4700 equals 4200 e to the, and again, T is now going to become negative 3 because that happened 3 months ago. So that'll be negative 3k. Okay, similar process, solve for k. We'll divide by 4200 on both sides, which should simplify to 47 over 42 e to the negative 3k. We can take the natural log on both sides to get the k out of the exponential. So we have the natural log of 47 over 42 equals negative 3k. Dividing by negative 3 or multiplying by negative 1/3 is going to say that k is negative 1/3 natural log 47 over 42. Let's plug that back in. So our value is going to be 4200 e to the negative 1/3 natural log of 47 over 42 times t. And you might look at this and say, wait a minute, you said that the natural log of anything between 0 and 1 is going to give us decay, but that 47 over 42 is actually greater than 1. It is, but the negative 1/3 out front actually makes the whole exponent a negative value. So it still is decay. It just has to be the negative exponent of the exponential to make it decay. All right, so there's our equation. Part C, what will the trade-in value be a year after the time the car is $4,700? A little bit tricky in the wording there. The $4,700 occurred 3 months in the past, but we want to know how much it's going to be 1 year from that point. Well, if you take away those 3 months in the past, that means there's still 9 more months to go. So the value that I have to plug into t is actually 9, because it's not from our time 0, it's from the 3 months in the past. So we actually have to do v of 9. If you had let the 4,700 be your time 0, then it would have just simply been 12 for the months. So if we plug in 9, we're going to get, you know what, I'm not going to write the whole thing out. No point. Just plug in the 9 for t, and you should end up with 2997.12. And this is one of the few times I will not actually go past the to the 3 decimals, because we are talking about money and we're not actually going to break this thing down into sub-cents. So $2,997.12, 1 year after the 4,700 time, or 9 months after our initial time. Part D, last part here. You plan to get rid of the car when the trade-in value drops to $1,200. When will this be? Again, the word when means we are solving for time. So we will plug in 1,200, set that equal to 4,200 e to the, let's see, negative 1/3 natural log of 47 over 42 times t. I am not actually going to run through the algebra of this one like I have in the past. You would divide by 4,200, take the natural log on both sides, and then divide by what's left in the parentheses. And here we will get that the time is approximately equal to 36.413. All right, that is plenty enough examples for this video. Day 2 actually just has a bunch more examples. There are probably 2 out of the 5 examples in there that are really important, including the last one. So if you feel really comfortable with all of this, you can probably skip through the other 4. I'm still going to do them for anybody who wants them, but the last example in Day 2 is probably the most important one to watch, because it's definitely something that we haven't talked about. All right, good enough for this video.